Hello everyone. In this video we will be discussing heat. Heat is a form of energy which enters or leaves a substance, changing its temperature or its phase in doing so. Just like the other forms of energy that we've seen in this course, heat is measured in joules. There are a few different equations for heat depending on whether the substance is changing temperature or undergoing a phase change. The heat required for a change in temperature is given by the mass of the substance times the specific heat times the change in temperature. Meanwhile, the heat required for a phase change is the mass of that substance times its latent heat. If the subject is changing phases between solid and liquid, we use the latent heat of fusion. Then if the substance is changing between liquid and gas, we use the latent heat of vaporization. The plus-minus signs on each of these equations depends on if heat is entering or leaving the substance. For example, going from solid to liquid, which is melting, or from liquid to gas, which is vaporization, both require heat coming into the substance, so we would use the positives. Meanwhile, if the phase changes are going in the other direction, we would use the negative for heat leaving the substance. For our last equation related to heat, if one or more substances are placed into an insulated container, then no heat will enter or leave that system. So any heat that does transfer between the substances must all add up to zero. In other words, there has been no net change in heat. Let's take a look at some examples to see how all this comes together. This question asks, how much heat is required to vaporize 500 grams of water at 60 degrees Celsius? When it comes to heat problems, a method that I've found helpful to keep track of all the different heats that could be possible is to draw a web diagram that takes you from your starting point to your ending point. In this case, we are starting with 500 grams of water, which is at 60 degrees Celsius. According to this problem, we know that we're going to be vaporizing this water, so what happens to it first? Well, before it can vaporize, the water has to reach its boiling point. So first it must be heated to 100 degrees. So our next step in this web diagram, we'll now change this 500 grams of water to be at 100 degrees. Only now that it's reached 100 degrees can we start vaporizing this water and turn it into steam. So we will undergo a phase change. We are still having 100 grams of this substance, but now the water has turned to steam. And during a phase change, our temperature doesn't change, so we are still at 100 degrees Celsius. By drawing my web diagram like this, where each different step of the process is a different point in my web, I can see that for every arrow I've drawn, there is a heat, Q1 and Q2, that needs to be calculated. Once I calculate both of these individual heats, I will simply add them up together to get my total heat that would be required. To get the heat Q1, I'm taking water at 60 degrees and heating it to 100 degrees. So I will use my changing temperature equation, which is mass times the specific heat times the change in temperature. The mass I know is 500 grams, though I would want to convert that to 0.5 kilograms. Now multiplied by the specific heat. The substance is water, so I will use the specific heat of water, which is 4,190 joules per kilogram degrees Celsius. And finally, multiply by my change in temperature, which is always calculated by doing final temperature minus initial temperature. So final will be 100 degrees in this case, minus initial was 60. Doing this calculation, I end up getting a Q1 of 83,800 joules. Moving on to the second arrow where I have Q2 labeled. This is a phase change. Water is turning into steam. I'm undergoing vaporization, so this should be a positive heat that I need. The mass is still 0.5 kilograms. Multiplied by the latent heat, in this case I want to use the latent heat of vaporization for water, which is 2.26 times 10 to the 6 joules per kilogram. Doing this calculation ends up giving me 1,130,000 joules. So to get the total heat required, I will now add Q1 and Q2 together, giving me a heat of 1,213,800 joules. as my final answer. For our next example, we have 100 grams of ice at a temperature of negative 5 degrees Celsius, dropped into 500 grams of water, which is at 20 degrees Celsius. If the container is insulated, what is the final temperature of the resulting water? This is now an insulated container problem, where two substances at different temperatures are mixed together. We know in this scenario that over time, these substances will reach thermal equilibrium, and everything will end up having the same final temperature, which is what we are looking for. What makes these problems a little bit more tricky is that each substance is going to be undergoing its own exchange of heats, which we have to keep track of before adding them all up to get zero. Once again, I recommend the web diagram approach, but now we have two starting points to keep track of, which will eventually converge into the same final temperature. For my first substance, I have 100 grams of ice at negative 5 degrees Celsius. Meanwhile, for my second substance, I'll write it off to the right to keep it separate. I have 500 grams of water at 20 degrees Celsius. Thanks to some information from the problem, I know that eventually I'm going to get to just water at some final temperature. So let's start with the ice and think how it can go to water. Right now the ice is at negative 5 degrees Celsius, so before it can melt, it has to get to its melting point at 0 degrees Celsius. So the ice first has to undergo a temperature change to reach still 100 grams of ice, but now at 0 degrees Celsius. Now that the ice has reached its melting point, it can melt into water, still at 0 degrees Celsius, since phase changes don't change temperature. Still 100 grams, but now it is water, still at 0 degrees. But now that it's water, it can safely heat up to whatever its final temperature is. So one more heating. I'm just considering the 100 grams that I started with on this side. It is still water, but now at some T final, which I don't know. So that's everything that I have to do on the ice side of things. What about the starting point of 500 grams of water on the right? Well, I know the water is going to stay water, and because of the ice, it's probably going to be cooled down by some amount. I don't know what that final temperature will be, but I know that I'm looking at still 500 grams of water, but now at some T final, which is the same T final that the ice will reach. Once everything mixes together, I will have a total amount of 600 grams of water at some T final, which I'm trying to figure out. But to find that final temperature, I need some equations. The one we will be using for an insulated container is that summing up all of our heats should add to 0, which means I need to know what all heat transfers will happen here. Again, since I've done this web diagram approach, every arrow I've drawn indicates a heat that I need to calculate. Heating the ice I'll call Q1, melting the ice Q2, heating that water will be Q3, and cooling the original water I'll call Q4. To calculate Q1, I am heating ice, so I will use the mass of that ice, which is 0.1 kilograms, times the specific heat of ice, which is 2090, multiplied by how much the temperature has changed, which is final 0 minus the initial, which is negative 5. I end up finding that Q1 is equal to 1045 joules. For Q2, that is a phase change. The ice is melting, so I will want to use a positive times the mass, which is still 0.1 kilograms. Now, since it is melting, I want to use the latent heat of fusion, which for water will be 333,000. And doing this calculation gives me 33,300 joules. Next for Q3, this is a temperature change. I'm taking water at 0 degrees to some final temperature. The mass is still 0.1 kilograms. Times now I need to use the specific heat of water, which is 4190. Multiplied by the change in temperature, which is T final. This time the final temperature is the one I'm looking for, minus the initial temperature, which is 0. Doing this calculation gives me Q3 is equal to 419 times that final temperature. And for our last heat here, Q4, This is now the 500 grams of water cooling down, so this is a temperature change. This time the mass that I'm using is the 500 grams, which is 0.5 kilograms, multiplied by the specific heat of water, which again is 4190, multiplied by the change in temperature. The T final is the T final that we're looking for, minus this time the initial temperature is 20 degrees Celsius. Multiplying this out will give me Q4 is equal to 2095 T final minus 41,900. Now that I have all of these heats, I can start plugging them into my insulated container equation. So adding them all up, so Q1 is the 1045 plus Q2, which is the 33,300, plus Q3, which is the 419 T final, plus Q4, which is 2095 T final, minus 41,900. Must all add up to 0. This now gives me an equation with the only unknown as the T final, which I can now solve for. Combining my T final like terms, I end up getting 2,514 times T final. Then combining all the constant terms, I get minus 7,555 must equal 0. When I move things around, I get the 2,514 T final is equal to 7,555, which when I divide both sides by the 2,514, gives me a final temperature of approximately 3 degrees Celsius. And with that, we'll bring our video on heat to a close.